Good day, grade 12 learners. Welcome to today's physical science lesson. My name is Thabo Mboweni. This lesson is brought to you by the Northern Cape Department of Education in collaboration with Pagama Research and Development. Today's lesson is on the knowledge area chemical change and another subtopic electrochemical cells. We are going to be focusing on the galvanic cell today. Let's get started. What is the prior knowledge? The knowledge that is needed for this lesson so that it can be understood. The grade 11 work that you need to have with you, that you need to have revised before you can fully understand the contents of this lesson. We need to revise the oxidation numbers as they are studied in grade 11, the rules for assigning oxidation numbers, and how to add oxidation numbers. We need to be able to explain the meaning of the oxidation number as studied in grade 11, and also assign oxidation numbers to atoms in various ions and molecules by using the oxidation number guidelines or rules as studied in grade 11. The prior knowledge continue, and we are going to look at the lesson objectives for today's lesson. At the end of this lesson, you need to be able to define a galvanic cell. You need to be able to define oxidation and reduction in terms of electron transfer. And we also need to be able to define oxidation and reduction in terms of oxidation numbers. We also need to be able to define the term oxidizing agent and reducing agent in terms of oxidation and reduction. And we also need to be able to define anode and cathode in terms of oxidation and reduction. And very important is that we also need to be able to define the term electrolyte. The lesson objectives continue. We also need to be able to state the potential difference. The potential difference of a galvanic cell in volts related to the extent at which the spontaneous cell reaches equilibrium. We are going to learn that our cell is going to reach the state of equilibrium, as you have studied chemical equilibrium. And we need to state and use the qualitative relationship between the V cell and the concentration of product ions and the reactant ions in a spontaneous reaction, namely the V cell, that is the EMF of a cell, decreases as the concentration of the products. It decreases as the concentration of the product increases, and the concentration of the reactant ions decreases until equilibrium is reached. I will repeat. The EMF of a cell decreases as the concentration of the product ions increases and the concentration of the reactant ions decreases until the cell reaches equilibrium. And at that point, we now have the V cell is equal to 0, and we say that the battery is flat. We still continue with the lesson objectives. We need to be able to describe the movement of ions in the solution. We need to be able to state the direction of electron flow in the external circuit, and we need to be able to write down half reactions that occur at the electrodes. We also need to be able to state the function of the Sol bridge as we are going to see it in the lesson. Very important. Baseline activity. At the end of this lesson, you need to be able to answer these questions. Let's look at the first question. Consider the electrochemical cell with the following cell notation. This is our cell notation. At the end of this lesson, you will be able to know the cell notation. And then we'll be able to see that in the cell notation, the first part, this is the first part of the cell notation. It describes the substance that undergoes oxidation. And we also have the second part of the cell notation, which describes the substance that undergoes reduction. And then we'll also be able to explain the meaning of those electrodes which are included there. So the question will say, which one of the following equations represents the cathode half-cell reaction? So from the cell notation at the end of this lesson, you should be able to see that the substance that undergoes reduction, it occurs at the cathode, and that should be the substance that should be the reaction that is happening at the cathode. You will be able to answer those questions at the end of this reaction, at the end of this lesson. The baseline activity continues. You should also be able to answer questions such as this. The diagram below represents a voltaic cell, that is a galvanic cell. Which one of the following correctly describes the movement of ions in the cell? We are going to explain this cell as the lesson progresses. And then at the end of this lesson, you should be able to answer the question on which one of the following correctly describes the movement of ions in the cell. The response to that question, as us in the baseline activity, just as the baseline information, the potassium chloride, in this case, which is an ionic substance in the salt bridge, makes or maintains electrical neutrality in the solution without mixing the solution. The chloride ions, which are negative, they will react with the positive ions, which are the zinc ions, and the positive potassium ions will react with the sulfate ions. You will understand this as we carry on with the lesson. So that is the response to the baseline activity in the previous slide. The baseline activity continues. Which one of the following reactions will proceed spontaneously under standard conditions? And you should be able to respond to this question at the end of this lesson. But as we look at the response, we will see in the next response that a spontaneous reaction is a reaction that proceeds on its own. A spontaneous reaction is a reaction that proceeds on its own without external additional energy. The lesson is going to explain that. So the standard conditions relate to the temperature of 25 degrees Celsius and the concentration of 1 mole per decimeter cubed. The prior knowledge also includes the following: the use of cell notation diagrams to represent a galvanic cell, as we have seen earlier in the previous slide. When writing the cell notation, the following conventions should be used. Now, the hydrogen, in this case, we must be able to see that the oxidation number of the H2 is 0, and the oxidation number of the H plus is +1. So this, in this case, indicates here that the oxidation number has increased from 0 to 1. And this half cell is treated just like any other half cell. So when writing the cell notation, you should be able to see whether the oxidation number is increasing or the oxidation number is decreasing. In this case, the oxidation number is increasing because it's moving from 0 to 1. Pay attention to the line that is drawn in between the H2 and the H+. The line means that there is a phase change from gas to aqueous. The cell terminals, which we call the electrodes, are written outside the cell. They are written outside the cell. If you look at this representation, the notation here, the electrodes are not indicated there. And then if we want to indicate the electrodes in this case, we would say the hydrogen and the H plus, and then outside would indicate the electrode, which is the platinum. So that is how we are going to write the cell notation, but let's continue with that. The active electrodes, which are the reducing agents, oxidized species, the oxidizing agent, and reduced species. So this explains how we write the cell notation. We will see that the oxidizing agent is a substance that undergoes oxidation. And then here, this is the oxidized species. So the one which has lost electrons. And remember, these lines means there's a phase change. And then we will have the oxidizing agent, which is a substance that undergoes reduction. And then here we'll have the reduced species, which is a substance that has gained electrons. So if we look in this example here, we will have platinum as the electrode for substances which are not metals, reducing agent, the phase change, the oxidized species, the salt bridge. The two lines in here indicates that there's a salt bridge, the oxidizing agent, and the reduced species. And then we put the electrode. Let's look at the example here. We have platinum here, which is the active electrode. And then we have the chloride ion with the oxidation number of -1. And then we have the oxidation number of 0 for the chlorine there. And then here we'll have the 0 oxidation number for the fluoride ion and the -1 for the other one. Now let's look at the oxidation numbers. The oxidation number of the chloride ion is -1 and that of chlorine is 0. You will see that there is an increase in oxidation number from -1 to 0. That shows an increase in oxidation number. And when we look at the second part, which is the fluorine, the oxidation number starts from 0 to -1. So this shows a decrease in oxidation number. So this substance on the left undergoes oxidation, and this substance on the right undergoes reduction. The substance undergoes reduction. This is the substance that undergoes oxidation. So when we write the cell notation, the most important part is that the substance on the left is a substance that undergoes oxidation, and the substance on the right is a substance that undergoes reduction. We must be able to see the increase in oxidation number on the left, and we must be able to see the decrease in oxidation number on the right. The active electrodes, the platinum, which is used in this example, is applicable only when the substances in question are not metals. If we look at the chlorine itself is not a metal, and the fluorine itself is not a metal, hence we use platinum as the electrode. Platinum is the inert electrode in this case. It does not take part in the reaction. It is only the metal which conducts electricity and allows electrons to flow. The prior knowledge also includes the following. We will need to predict the half cell in which oxidation takes place by using the standard reduction potential table. And we also need to predict the half cell in which reduction takes place. And for that, we use the standard reduction potential table. And we will also need to be able to work out the overall cell reaction. So that is what the lesson is going to discuss as we carry on. The standard reduction potential table, you have looked at it in grade 11. We are also going to look at it in grade 12. And we are going to predict the substance undergoing reduction and the substance undergoing oxidation. And we are also going to use it to calculate the EMF of a standard galvanic cell. We are going to use the positive value on the standard EMF as an indication that the reaction is spontaneous under standard conditions. So when we do the calculations of the EMF and then the answer that we get, perhaps is positive 1,2 volts. So because this value is positive, this will indicate that the reaction is spontaneous under standard conditions. We continue with the lesson. We need to be able to write down the standard conditions under which electrode potentials are determined. We need to be able to describe the standard hydrogen electrode and explain its role as a reference electrode. The standard hydrogen electrode is going to be used as a reference electrode, and we are going to explain its role there. We are also going to explain how the standard electrode potentials can be determined using the reference electrode, which is the hydrogen electrode. The hydrogen electrode is the reference electrode, and then we are going to explain how it can be used to determine the electrodes of other reactants. We are also going to state the energy conversion regarding the positive and negative values. The galvanic cell. The galvanic cell is also called the voltaic cell. It's an electrochemical cell that converts chemical energy to electrical energy. A galvanic cell is an electrochemical cell that converts chemical energy to electrical energy. So that is how we are going to define a galvanic cell. This is the definition of a galvanic cell. An electrochemical cell that converts chemical energy to electrical energy. Galvanic cells can be said to be spontaneous due to the fact that when we calculate the E0 cell of the galvanic cell, we get a positive value. So because we get a positive value, we can say that they are spontaneous. They occur on their own without additional energy being added. Galvanic cells or galvanic reactions are said to be exothermic in the sense that they release energy. Energy is released from the system to the surrounding, and hence we refer to galvanic cell or galvanic reactions as exothermic reactions. Now, we need to be able to define the oxidation and reduction, which are acronyms which are embedded in the word redox. So redox is an acronym that can be expanded to reduction and oxidation. We need to be able to explain these terms, reduction and oxidation, in terms of electron transfer and also in terms of oxidation numbers. Now, electrons will easily be lost by metals and gained by non-metals, which is very, very important as we proceed with the lesson. Metals have excess electrons which are delocalized, and because of that, the metals will easily lose electrons, and the non-metals will easily gain electrons as we proceed. Metals are good conductors of electricity because of these free electrons which they possess, which are delocalized. Therefore, they are good conductors of electricity. Now, let's define oxidation and reduction. Firstly, in terms of electron transfer. Oxidation in terms of electron transfer is the loss of electrons. Oxidation in terms of electron transfer is the loss of electrons, and reduction in terms of electron transfer is the gain of electrons. So if the examiner says define oxidation in terms of electron transfer, oxidation is the loss of electrons. If the examiner says define reduction in terms of electron transfer, reduction means the gain of electrons. Oxidation and reduction always takes place simultaneously, and one cannot occur without the other. Now, just to help you remember the definitions, we have these acronyms here. The first one is oil, which is red. Oxidation is the loss of electrons. And then we have RIG, which says that reduction is a gain of electrons. So you can use that in case you forget those definitions. Oxidation numbers. We want to define oxidation and reduction again in terms of oxidation numbers. Oxidation defined in terms of oxidation number is the increase in oxidation number. How are we going to see that? Let's look at this half reaction. If we look at the oxidation number of zinc here is 0. The oxidation number of the zinc ion on the other side is 2 plus. So the number moved from 0 to 2 plus. So this is an increase in oxidation number. So whenever we see the increase in oxidation number, that means the substance is undergoing oxidation. Let's go to reduction. Reduction is defined in terms of oxidation numbers as the decrease in oxidation number. How are you going to see that? If we look at zinc on the left-hand side, its oxidation number starts from 2 plus. And then we look at it on the right-hand side, the oxidation number is 0. So this one, in this reaction, the oxidation number moved from 2 plus to 0, which is a decrease. So that's how we are going to spot the decrease in oxidation number. And whenever we see a decrease in oxidation number, we know that the substance undergoes reduction. Just a recap, oxidation in terms of electron transfer is the loss of electrons. Reduction in terms of electron transfer is the gain of electrons. Oxidation in terms of oxidation numbers is the increase in oxidation number. And reduction in terms of oxidation numbers is the decrease in oxidation number. Oxidizing agents and reducing agents. The oxidizing agent is a substance that gains electrons and undergoes reduction, and we say that it is reduced. I will repeat. The oxidizing agent is a substance that gains electrons. It undergoes reduction and it is reduced. The oxidation number decreases because this substance is reduced. We have seen the definition of reduction in terms of oxidation numbers. Let's look at the reducing agent. The reducing agent is a substance that loses electrons and it undergoes oxidation. And because it undergoes oxidation, we say that it is oxidized. We are going to see that with the oxidation number that increases. The electrode. What is an electrode? An electrode is a solid electric conductor that carries current to non-metallic part of the circuit. An electrode is a solid electric conductor that carries electric current to non-metallic part of the circuit. The anode is the electrode where oxidation takes place. These are the definitions. We are defining an electrode and we are also defining the anode. The anode is the electrode where oxidation takes place, and an electrode is a solid electric conductor that carries electric current to non-metallic part of the circuit. The cathode. What is the cathode? A cathode is an electrode where reduction takes place. A cathode is an electrode where reduction takes place. Anode and cathode. We want to know what is happening at the anode and we want to know what is happening at the cathode as electrodes. Now, at the anode, we get a substance which is called the reducing agent. We know that oxidation takes place there at the anode, and the substance that is at the anode is oxidized. If I repeat, at the anode, we will get the reducing agent. The substance that is there on the anode compartment undergoes oxidation, and that substance is oxidized. at the cathode. The cathode is the electrode. That's where we are going to get the oxidizing agent. And then the reaction that is happening there is a reduction reaction, and the substance in the cathode compartment undergoes reduction. And we say that that substance is reduced. Let's define the electrolyte. What is an electrolyte? Electrolyte is an ionic substance of which in an aqueous solution that contains ions, and a substance that dissolves in water to give a solution that conducts electricity. So we can define it in two ways. We can define it as an ionic substance of which the aqueous solution contains ions, or we can define it as a substance that dissolves in water to give a solution that conducts electricity. A galvanic cell. A galvanic cell consists of two electrolytes separated by a salt bridge. So we are going to see one container and another container. In one container, there will be an electrolyte, and in another container, there will also be an electrolyte. And these two containers will be connected by a salt bridge. And then we are also going to have electrodes there. So just to give you a picture, a galvanic cell consists of two electrolytes. The electrolytes are inside these beakers, separated by a salt bridge. Salt bridge is we can use a cotton as a salt bridge, which is dissolved in water to transmit the ions. Electrodes are connected to a galvanometer or a voltmeter. So these are the electrodes. These electrodes, they are connected to a voltmeter or a galvanometer. And this part of the circuit, that's what we call the external circuit. So this part of the circuit where the electrodes connect to the voltmeter or galvanometer is referred to as the external circuit, and the part where ions move through the salt bridge is referred to as the internal circuit. The salt bridge consists of salt solutions which allows movement of ions between two half cells. So the salt bridge will consist of an ion. Example in this case can be potassium chloride. The potassium chloride will separate into its ions, forming the potassium ions and the chloride ions, which move into the different half cells to neutralize the circuit. So the movement of these ions is between these two half cells. Some of the ions, the positive ions, will move in one direction, and the negative ions will move in the other direction. In a galvanic cell, the anode is negative. In a galvanic cell, the anode is negative, is the negative electrode, and that is where oxidation occurs. The cathode in a galvanic cell is positive, and that is where reduction occurs. This is very important. In a galvanic cell, the anode must have a negative charge, its electrode, and that is where oxidation occurs. The cathode will have a positive charge, that is the charge of the electrode, and that is where reduction occurs. The standard reduction potential. We are going to use the standard reduction potential to determine which substance undergoes oxidation and which substance undergoes reduction in an electrochemical reaction. Now, if we look at the standard reduction potential, we are looking at the 4B. There are two of them. There's a 4A and the 4B. They are the same. The difference is that on the 4B, we are going to have the lithium as the first one, and then we are going to end with the fluorine. Now, we want to look at how do we read the standard reduction potential and how we are going to use the standard reduction potential to determine the substance that undergoes oxidation and the substance that undergoes reduction. Now, when we look at the standard reduction potential, we will see the lines on the sides with arrows. The line on the right here says increasing, reducing ability. Increasing, reducing ability. We know the reducing agent, and we know that the reducing agent undergoes oxidation. So now, this table tells us that lithium has the greatest reducing ability than all the other substances on the table. So this indicates that if lithium is to react with any other substance in the table, lithium will undergo oxidation. And any substance on the table should undergo reduction. Let's take, for example, we take zinc on the table, and then we also take nickel. The arrow says, as it goes up, increasing, reducing ability. So now, if zinc is in a cell with nickel, zinc, because it has a greater reducing ability, will undergo oxidation, and nickel will undergo reduction. And from this, we can come up with two half cells of the reaction, where the substance that undergoes oxidation will now be written in reverse. How do we write it in reverse? We start writing it from the right to the left. So this is how we're going to write it. This is going to be Zn, that was on the right. We are no longer using two arrows, one arrow. Then we are going to have Zn2 plus and 2 electrons. And from this, we see that the oxidation number here moved from 0 to 2 plus. This indicates that this substance undergoes oxidation. How did we know that it undergoes oxidation? From the arrow that goes, that points upwards, it says increasing, reducing ability, meaning that the substance at the top will have a greater reducing ability than the substance at the bottom. Therefore, zinc undergoes oxidation and nickel will undergo reduction, and the half reaction for that is going to be written as it is from the table with the one arrow. So we are able to tell which substance undergoes reduction and which substance undergoes oxidation from reading the table. We can also take another example. If we take sodium and lithium, we observe that the arrow pointing to the top says increasing, reducing ability. Therefore, lithium will have a greater reducing ability than sodium. Therefore, the lithium is the one that will undergo oxidation. And because of that, the reaction that undergoes oxidation from the table is going to be written in reverse. We are going to write it as Li, and then we put one arrow instead of two. Then it changes to Li plus with one electron. So that is our oxidation half reaction. And then the sodium is going to be the one that undergoes reduction. Then it's going to be written as it is, Ni plus with one electron that changes to Na. And this is our reduction half reaction. So that is how we're going to use the standard reduction potential table.